The detection of gravitational waves is no longer hypothetical. In 2015, to enormous excitement around the world, the field of gravity waves became real, as the first waves were detected with the Ligo experiment. A new field of science has been born, and we're waiting to see how it plays out. Here is the signal that the two Ligo experiments in Hanford and Livingston detected in September 2015. We see the characteristic ringing or chirping sound of two black holes spiraling into each other to form a new massive black hole. The signal, crucially, was detected at both Ligo experiments with a delay of 700 milliseconds. The strength of the two signals, plus their waveform, nails down that it must be a black hole in spiral. It's a highly specific waveform predicted by general relativity and simulations of black holes coalescing. The difference in the strength of the two signals and the time delay gives a very crude direction on the sky, in this case coming from the southern sky somewhere near the Magellanic Clouds. The strength of the signal, plus the knowledge of the mass of the black holes that we're combining, and the fact that gravity waves diminish with the inverse square of distance, just like light, gives a rough distance. And in this case, the distance to this event was 1.1 billion light years. So in some anonymous galaxy, halfway across the universe, two black holes coalesced and produced a signal detected by the two LIGO detectors. In the initial LIGO detection, the original black hole masses that were published have been revised upward by better calculations and theoretical modeling. And it now appears that the two black holes that coalesced were 30 and 35 times the mass of the Sun. They combine to form a black hole of about 62 times the mass of the Sun. So fully 3 solar masses of energy were released as gravitational waves and left the system. This is an extraordinary event because these are very large masses for black holes. In fact, theorists have been challenged to explain how two such massive black holes could exist, because the initial stars that would have led to a black hole of 30 or 35 times the mass of the Sun must be 60, 80, even 100 times the mass of the Sun, about as massive as a star can get. The first LIGO detection was extraordinarily exciting. Of course, it excited physicists and scientists of all stripes, but it made the front page headlines of all the news services. This is the way we can detect mass directly in the universe without the use of radiation. An extraordinary innovation. And as I mentioned, a new field of science has been born. The first detection itself was exciting within the project because it happened within days of the first science run of LIGO at its full sensitivity. In fact, many people in the project didn't know of the detection, and they were suspicious of it. So many checks were made to be sure it was a real signal. It turned out that the project leaders had sort of salted the mine by putting in fake signals into the data stream just to see if they could be detected. And many of the people in the experiment thought this first detection was one of those fake signals. But when the timing of those fake signals was revealed, it was clear that this was a real detection out there in the universe. One gets you going, but two makes you confident you have a real new scientific project. And the second LIGO detection was announced in the middle of 2016. Not quite as dramatic a signal, representing the coalescence of two smaller black holes, 8 solar masses and 12 solar masses, but in an even more distant galaxy, at about a distance of 1.4 billion light years. There's a hint of a third signal, not sufficiently strong that the team are willing to claim it as a detection. But we can confidently predict that with LIGO at full strength, it will detect between 15 and 20 gravitational wave events per year, and will start to be able to do statistics on black hole coalescence in the distant universe. The accolades have already started to come in for the 3 gurus of the gravity wave experiment. Recognize this is a huge project with close to 1,000 investigators internationally. But really, LIGO was the brainchild of 3 people. 1, Ron Drever, fellow countryman, a Scot. 2, Kip Thorne, Caltech theorist, well known for his work on black holes. And Rainer Weiss, based at MIT. This is fundamentally an MIT-Caltech collaboration. These 3 visionaries foresaw decades ago that this was a potentially feasible experiment. And they worked through the decades when there was no funding, when there was a lot of skepticism, when the National Science Foundation wouldn't give them any money, and when other physicists doubted the experiment was possible. They won the Kavli Prize in Astrophysics in 2016, and many people suspect that a Nobel Prize is in the offing. We can see from this map of the position on the sky of the first two LIGO detections that two LIGO detectors simply doesn't pin down the place on the sky where the event occurred with any kind of accuracy. There's no way for optical or X-ray or radio astronomers to go out and find what the original source was, especially when they're so far away. There are thousands or hundreds of thousands of galaxies out to distances of 1 billion light years within these error ellipses. So we need more LIGO experiments to get extra detections of the same event and pin down the accuracy on the sky, sufficient that it can be followed up. Those other detectors are underway. There's already one in Europe and soon to be a second, and the Japanese and the Indians are building their own gravity wave experiments. So soon there will be a network of gravity wave probes. LIGO will still be the most sensitive, that will allow us to pin down where these events occur on the sky. And that will be an enormous boost in interpreting what's going on. LIGO has also given an enormous overall boost to the field of gravitational wave astronomy. Remember that LIGO has sensitivity that's bounded in one direction by the Earth's geological activity. In other words, frequencies of gravity waves much less than about 1/10 of a hertz cannot be detected due to the rumblings of the Earth. Gravity waves with frequencies more than a few hundred hertz can be detected because of shot noise, a fundamental limit in the detectors. And so there's a motivation to look at other regimes of frequency for gravity waves, in particular for the longer, slower gravity waves that would be caused by more massive black holes coalescing. The key experiment here is called LISA, Laser Interferometer Space Antenna. It's the idea of a free-floating set of Michelson interferometers in space doing the LIGO experiment in zero gravity, and of course with no disturbance from the Earth. The LISA designs were put into place several decades ago when gravity waves were pie in the sky. But recently, LISA has an enormous boost and some funding, particularly from the Europeans, for a Pathfinder experiment. It appears that there are no technical obstacles to a LISA-type experiment being put into orbit. With a LISA-type experiment, we'll be able to detect the coalescences of the massive black holes that occur in galaxies. And since galaxies in the universe have grown over cosmic time by mergers, we know that the massive black holes at the heart of every galaxy will have coalesced as they grow, presenting an enormous set of signals for a LISA-type facility to detect. Another method that can be used is pulsar timing arrays, because as a gravity wave washes over a pulsar, it very subtly alters the spin rate. Remember that pulsars are the most exquisite clocks known, with precisions of 1 part in 10 to the 17. So with a network of pulsars being monitored with exquisite timing, it's possible to detect the way they're altered by gravity waves passing over them, and then pin down the orientation of the original incoming gravity wave and its strength. This is yet a third technique, which relies on having very precise timing and large arrays of pulsar detections, which occurs at radio wavelengths. With these three different types of gravity wave experiment, we are destined to learn an awful lot about the universe in the next few decades. A new field of science has been born. LIGO made its first detection in 2015 and followed it up with a second detection in 2016. Gravitational waves have been and can be detected by these two exquisite experiments, and other experiments are going to follow, including space-based versions of LIGO, which can detect the coalescence of massive black holes.